This is Dr. Hal Needham with a brief presentation called Why Use a Data-Driven Storm Surge Analysis. So storm surge is a catastrophic natural hazard. Traditionally, to understand storm surge risk, we've used models. In the US, some of the most popular storm surge models are ADCIRC and SLOSH. So ADCIRC is often used by the scientific research community, and researchers can actually adjust some of these inputs like hurricane track or hurricane wind speed, and the output or the result of this model will be maximum water levels along the coastline or in an open area of water. SLOSH is perhaps best known as an operational hurricane model that the National Hurricane Center will use to predict maximum water levels along the coastline as an actual hurricane approaches the coast. These models are very popular and very useful for understanding what could happen in a hurricane and in general our long-term risk analysis. Today, however, I wanted to introduce the USurge era, the dawn of data. And what I mean by that is the dawn of data-driven analysis. So for the first time through the USurge project, we're able to create comprehensive storm surge data sets that go back far enough in time that we're able to use them to conduct statistical analysis that tell us something about our risk for coastal flooding along the coastline. This is a time series of storm surges that occurred in South Texas at South Padre Island from 1900 to present. And so this blue polygon on the bottom shows sea level rise over time from 1900 to present. And these blue circles show maximum water levels from hurricanes and tropical storms since the beginning of the 20th century. These are actual events. In fact, at South Padre Island, the three highest events on record were the water levels from Hurricane Allen in 1980, the water level from the unnamed hurricane of 1933, and Hurricane Beulah in 1967 produced the highest water level on record as the storm surge reached approximately 12 feet. And again, these were actual events that occurred. These weren't theoretical or hypothetical events. For example, this is a picture of the flooding from Hurricane Beulah in 1967 as a 12-foot storm surge slammed into the South Texas coast and heavy rain occurred inland. Statistically, we can run analysis to actually take these data that occurred that we looked at in the time series, and we can actually run statistical analysis to tell us something about our long-term vulnerability. So this analysis here is called a log linear regression method. And let me explain what that means. The log stands for logarithmic. So look at the x-axis here along the bottom of the graph. We see 1, 10, 100, and 1,000. So this is time or return period in years, and the major breaks are logarithmic, meaning they go up by a factor of 10. Look at the y-axis. The major breaks here all go up by 2, and this is storm surge magnitude in feet. This is linear. They all have the same amount of distance between each of the major breaks. And what I've done on this graph, all of these blue diamonds are the positions of actual storm surge events. So Hurricane Beulah, again, was the highest event in 117 years. So I can go here on the graph over to around 117, and I can go up to 12 feet, and I can plot Beulah on the graph right there. Well, the 1933 hurricane produced a storm surge level of 11.2 feet. So that's here along the y-axis. And then on the x-axis, that was the second highest storm surge level in 117 years. So we can take 117, divide it by 2, and we can plot it. That's about a 58-year event. So we go over to 58, we go up to 11.2, and this diamond represents the 1933 event. And so on and so forth. Every one of these blue diamonds is an actual storm surge event. The regression line, or the black line here, is the line of best fit. And this line is used to take all of the data into consideration to predict what we think an extreme water level would be. For example, the 100-year water level. In fact, if we go to 100 and we go up and see where this black line bisects the 100 line, it's right around 12 feet. So according to this analysis, on average, every 100 years, we should expect the water level to equal or exceed 12 feet in the South Padre Island area. Data-driven analysis like this is really useful, especially if models are under-predicting water levels. So imagine if a storm surge model predicted the 100-year water level at South Padre Island to be 10 feet. We would say that likely that model is under-predicting because we've had 2 events in the period of record exceed 10 feet, and also the regression line, taking into account all of the data, says that the 100-year event is around 12 feet. And so data-driven analysis comes from a different perspective, but it can provide us with really valuable information. So Perhaps talking about models and data with storm surge and coastal flooding is a little bit confusing or abstract to you. If that's the case, I wanted to provide a brief example of data and modeling from our everyday life. And sometimes I like to use the example of transportation, because almost every day we leave our homes and we go somewhere. And when we get out on the streets and we walk or ride a bike or get in a car, we basically model how to get from point A to point B most efficiently. And what we want to avoid is a traffic jam like this. And in fact, this brief story I'm going to tell you is called Hal's Traffic Dilemma. It's about a time this past summer when my transportation model didn't work so well. So let me tell you the story. Last summer, I lived on Galveston Island here along the Texas coast. Galveston is about 50 miles southeast of Houston. I had to travel late on a Friday afternoon from Galveston up to Hobby Airport, Houston Southern Airport, to rent a car. And so this trip typically takes about 45 minutes if there's no traffic. However, this was Friday afternoon around rush hour. And so a friend took me up there and we anticipated it would take a little bit longer, and we were right. So without traffic, I'm making a little graph here, a little table. I'm saying if there's non-rush hour traffic, it takes about 45 minutes. Friday afternoon, it took us about 55, and that's about what we expected. But my modeling question here, and these both were observed. You know, the non-rush hour, I've driven that many times. Friday afternoon, we drove that. It was observed. But Sunday, I had to model. And I didn't think of it as modeling. I just thought of it as making a decision. I needed to return the rental car by 5 p.m. on Sunday afternoon. And so the question I asked is, what time do I need to leave home in order to get to the airport by 5 p.m.? Well, I made an assumption, and that's what we do every time we get in the car. We make assumptions about how the real world works. I thought that Sunday afternoon would be a lot like non-rush hour traffic. So I thought it would take me about 45 minutes. I certainly thought it won't take as long as Friday at rush hour. However, when I got in the car and got on the highway, I saw a scene like this. I saw a lot of bumper-to-bumper traffic. At first I thought, well, maybe there's an accident. But as I looked around, I noticed something about the cars around me. I saw a lot of fishing rods and surfboards and sunglasses and sunscreen, and I noticed there were a lot of people coming from the beach. And that's when I realized there wasn't an accident. This was actually a pattern that occurs on weekends in the summertime. So you see, Houston is the fourth largest city in the U.S. It's about 4 million people, and a lot of those people come down to Galveston Island on weekends in the summertime to go swimming, to go fishing, play in the water, cool off. And on Sunday afternoon and evening, we have tens of thousands of people going back to Houston, and so we get these huge traffic jams. And so I didn't think of that in my model. I pictured Sunday afternoon. In most places I've been, Sunday afternoon usually is not very congested, and that was an assumption I made that was wrong. And so actually what happened was I got caught up in recreation traffic, but my model did not include that. So I was late. I thought it would take me 45 minutes. But in reality, it took me 65 minutes. So I was about 20 minutes late. So this showed that my model was off by about 50%. But when I actually drove the route, I was collecting data, so to speak, and I was improving my model. If I have to take that trip again, I'll give myself more time in the future. So validating models with data. We inevitably need models, and we use them every day. Models are only as good as our assumptions, though, or the input. So we have to make assumptions when we go to a new city, when we travel different places, but those assumptions will determine how good our model is. And then finally, data, driving the route in this case, reveals model error and helps me improve the model for the future. So one of my concerns when I get out and I work with coastal communities is that a lot of communities will say, we did a storm surge modeling project a few years ago, so we don't really need a data-driven approach, because I'm a big data guy. I've worked with storm surge data now for about 9 years. And inevitably, a lot of coastal communities will say, oh, we already did that. And their assumption or their perspective is that risk analysis is something you do once, and then you're done with it. You fund a project, you do some risk analysis, and you never have to really consider that again. However, my concern with communities that have done a modeling project is that it's like they're saying it takes 45 minutes to get to the airport, when data that are now available say it takes 65. So how do we know, for example, in a coastal community how vulnerable we are? We need models, but when data become available and when the science improves, we need to use that additional information to improve our analysis. So this is good news, though. I'm really think that it's good for communities to use a data-driven analysis, and 2 reasons why that's very possible to do. For one, data-driven analysis is very affordable. So modeling efforts can range in cost from, I don't know, $50,000 up to several $100,000, depending on if you need a supercomputer, if you need a team of scientists, if you're doing statistical analysis, modeling, geospatial analysis. Depending on what you're doing, we could be looking at hiring several scientists, at using supercomputing in the case of AdCirc sometimes. And the cost of this can run up well over $100,000, especially if we're working with a university. Universities will often take about 40% right off the top to cover their overhead. And so if you get a $100,000 grant, you really only have $60,000 to hire a scientist to help you with this project. Data-driven analysis, though, we can do much cheaper. In fact, USurge can conduct data-driven analysis, that's statistical analysis, sea level rise analysis, and also geospatial analysis for your community for $4,800. Now, how are we able to do this so cheap? Well, really two reasons. For one, we use a really efficient, I would say, business model. We don't have overhead, so we don't have office space to lease. We're not paying an electricity bill. Really, we're a team of scientists that work independently on laptops, and occasionally we'll meet face-to-face, and often we'll do conference calls and video calls. But because of that, we aren't paying overhead, so we can keep our costs down, especially compared to, say, government or university services. The second thing as well is that we're using an efficient model that uses economy of scale, if you will. And when you want an analysis from USurge, basically we'll give you access to a password-protected website. You can log into that website, and when you're looking at the analysis for your community, dozens of other people are also using that analysis. So because we're not using old, paper reports that are customized just for one end user, we're able to really provide this to more people, and this brings down the price for everyone. The second reason that data-driven analysis can be really efficient and good for you is that it's very rapid. So again, a modeling effort can take anywhere from several months to over a year. If you're working with a university or government, it could take 3 or 4 months just to get a grant approved. And then often if we're working with a team of scientists, it could take another 6 months on top of that. Really, on a low estimate, I put 6 months for a modeling study. Data-driven, we could do much cheaper. Our longest data-driven analysis for your community would take us about 3 weeks. Again, I've been doing this for nine years. I have a lot of information and a lot of resources available, and so does our team here. And worst case scenario, it would take us about 3 years to do this. However, in a lot of cases, we already have a website complete for your community, and we can provide information within the day or within 2 days or so. So data-driven analysis is very rapid, and it's very affordable. And again, it's based on the real world, on observations that have actually happened, and so it provides a different angle, and often a more accurate angle than modeling can do. Although this presentation is coming to an end, the party is not over. Reach out to me. Send me an email at hal@marineweatherandclimate.com or visit our website at www.usurge.net. Thanks again for tuning in, and make sure you check out our other videos where we talk about where the USurge data come from and where we're going in the future. Well, thanks again for your attention, and have a great day.